Okay, good afternoon. Today, I'd like to give you discussions about the first order ODE. There are the first one we after I introduce you about the solution curve and also um, direct integrations. Now I would like to introduce you another method to solve the ordinary differential equations. You can see from the slide, um, yeah, the topic is a separable variable. So if we have, um, okay, so if we have dy per dx is equal to function of xy, or we can write like this one, gx. So the differential equation we can write like this one: dy per dx is equal to gx. So it can be solved by the integrations. It's like direct integration. I mean by using integrating both sides. All integrates of dy per dx is equal to integration of gx. So we can get this one. After we integrate this one, we can this one, y is equal to integral of gx dx. So the result is gx plus c. So for example, we have this equation dy per dx is equal to 1 plus e quadrat x. Then we integrate both term. This one we integrate this one and another this one. So we can get these solutions: x plus a half of e quadrat x plus c. Okay. So what is the separable equation? So the first order dA of the form of d1 dy plus per dx is equal to gx hy here. So it's said to be separable or to have a separable variable because we have here dy per dx and another is gx and hy. So okay, if we rewrite the above equation, I mean that dy per dx is equal to gx hx like this one. So we can write like this one. Consider that py is equal to 1 per hy. So py is equal to dy per dx is equal to gx. Okay. When hy is equal to 1, so hy is equal to 1. So 2 are reduced to 1. Okay, this one. Reduced by this one, okay? If hy is equal to 1. Okay. And then if y is theta x is a solution of 2, so we must have p theta x and x equal to gx. And if we make integration, integral of p theta x theta accent x dx. Okay. And dy is equal to theta accent x dx. Okay, so we can write this equation 3 by this one become dy. So py integral of py dy is integral of gx dx, or hy is equal to gx plus c. Okay, so this is the example. So if we have this mathematic like this one, 1 plus x dy minus y dx is equal to 0. So we can write like this one: 1 plus x dy is equal to y dx, right? So dy per y is equal to dx per 1 plus x, this one. So we make integration of two terms, the left term and then a right term. So integral of dy per y is equal to integral of dx per 1 plus x. So ln y is equal to ln 1 plus x plus c1. So y is e ln 1 plus x plus c1 and equal to e ln 1 plus x dot e c1. And then we can write this equation by using this 1 plus x e c1. And the result is plus minus e c1 multiplied by 1 plus x. So we can replacing plus minus a e c1 by c, so we can get that y is equal to c1 plus xy. We can replace e c1 become c because this is the constant, right? And also this one also a constant, so we can replace by using this one. Okay. So you can also follow the example number 2 here, and then we can write the solutions. Okay. Also example 3. So the first one that you have to remember that in this separable variable you have to separate between two variables. Is this one. We have y and x, and here y. So we have to collect y in one term, left term of left side here, and x in another side. So after we collect in this term, so we just make it integral. So because of this is d1 per y quadrat mean 4, so we can write this term by using this one, 1 over y quadrat minus 4 dy here is equal to dx. So this in the box we can make a separation like this one for too easy, so we can get the ln like this one. So we can get this one x plus c1. So we can solve this equation by using this one. Okay, and then we can write like this one. Okay, and also in example 4, you can solve by using the equations. And okay, I have another example here. So find the solution of xy per x plus 1 is equal to dy per dx. Okay, so how to find these equations? So we have to make a separations. So we can see that this is the x, right? And also this also x, and another this is y, and this is y. So we collect x in left side and y in right side, or extra, up to you. So in this case, I collect x in left side and y in right side. So x is equal to x per x plus 1 dx is equal to dy per y. Okay, so here we have x per x plus 1. So we can write this in another term like this one, x plus 1 minus 1 per x plus 1. Yeah, this is the 0 here, so we can write like this one. So is equal to x plus 1 per x plus 1 minus 1 per x plus 1, or 1 minus 1 per x plus 1. Okay, so we can write x per x plus 1 is equal to this, 1 per x plus 1. So here we can write that we can make integrations. 1 minus 1 per x plus 1 dx is equal to integral of dy per y. Okay, so it's equal to, we make integration of 1 according like this one. So this like integral of 1 minus integral 1 dx minus integral of 1 per x plus 1 dx is equal to integral of dy per y, like this one. Okay, so it's equal to integral of 1 dx is equal to x minus ln of x plus 1 is equal to ln y plus k. Okay, and k is the constant of the integrations. So the x is equal to x is equal to ln x plus 1 plus ln y plus k. So this equal to ln ky. Okay, so sorry, this one is okay. Okay, I made a mistake here. It must be ln also, ln k, and also it is ln k. So ky x plus 1. Okay, so we get that ex is equal to ky x plus 1, like this one. So this is another example for separable variable. Okay, I think this is enough for these methods. See you in another method for ODE. Good afternoon.